Okay, everybody, welcome on in. We'll get started here. So welcome, everybody. I haven't seen any questions, so I assume we're moving ahead successfully. If you need to talk to me after class, it's a great time. There's office hours actually right after class today. Otherwise, I will keep moving us ahead, filling in information. Remember, as always, right, I always feel like I have to say this a bunch of times because some students forget, but also it's just an important part that you understand that I will not be able to cover even a lot of the topics that, show up on the homework. So, I cover the stuff that I think is most important and sometimes most confusing for students. So I try to point those things out so that the easier concepts, hopefully you can get from the video, right? And trying to give you some kind of the underlying stuff that can be missed from just watching those videos. Okay, a couple things. So as you saw, as many of you saw from the announcement that I made in class, you can take the survey now. So you go to the end of chapter 2. So you can see here chapter 2. You go to the end of that. It says take the survey. You click it, and there's a link here. All you have to do is click that link and take the survey, right? We've had not very good turnout so far. So it would be good if we could do better. Basically, of the 35 of you who signed up for the homework and are actually, participating in the course, 15 of you took the survey. So that means we have 20 people that are kind of holding up the process. So it would really be good if those 20 people could get in there and take that survey, because the sooner I can release the information, that means some people can actually start thinking about how their project should be, right? So you start thinking about the ideas that we're learning in our lessons and in the videos that you're watching, and the lessons that are here on Canvas. Start thinking about that while you have the project, and then it's easy because you can just switch over and go, oh, they're talking about z-scores? Ooh, I think I know some spots where I could use z-scores in my project, and then you hop over and you do that now. That's a lot easier than trying to remember 12 weeks from now. Go, wait, what was a z-score? I have to go back and learn what a z-score was again in order to calculate it. You can just get into that kind of stuff now and prepare it. So please do that, right? At some point, you'll get cut off, and if we don't have good enough numbers, that means everyone's project is like your numbers are going to be kind of bad. Like right now, our sample size is too low, right? All your data for everyone is going to look bad if all we have is 15 people in our stuff. Your histograms aren't going to look good. There's all sorts of issues. So good job to the 15 people who went in there and took the survey. To those of you who have not, please get it done, right? It's one of those things that's easy to forget, and then you move on with the rest of your life, till the next time we're in here, and I'm telling you to please take the survey. So please get in there, try to get that survey taken so that, we really want to see those numbers. Like, we don't want to see them much lower than the class that we have, right? We have 35 people participating. It'd be really good if we could see 35 people taking the survey, because that's kind of even on the low end of being able to do good stuff, but it'll work, right? But even when it drops, like in the summer class, I had less students, and we had 25 students take that survey, and it wasn't great. It definitely could have been better, right? I think it was harder because people's, you're not going to get your normal distribution showing up and that kind of stuff. It just makes it harder to deal with the data, harder to make interpretations. So it's just better. So if we could get 35 of you in there and take that survey, which is the number of people sort of still showing up and participating in the class, that would be great. So it's not just that you're doing doing some work that you need to do. Oh, I don't have a water this morning. I'll go grab one in a second. You're really you're helping the entire class. Each of you left, when you take the survey, you're making it better for everyone, including yourself. Right? Your own data is going to look better because you'll have more people taking the survey. So please try to do that. Okay, please try to step up and get that done. It's just right down here. Really, honestly, I forget how many questions there are, but it shouldn't take you longer than like 8 minutes, 10 minutes, something like that. We're not talking about a lot of time here, and you guys are all going to be, you guys and gals and everybody's going to be working on this for a long time. Throughout the entire semester, you want it to be as easy as possible. And the larger our sample size is, the better it's going to be for you, right? That's one of the, and this kind of gives us a moment to talk about sample size, right? Sample size is really important when you're collecting data. Generally, a larger sample size is better. There's a few instances where it's not, but the more people in your sample size, like if you get extreme, right, where you've sampled almost the entire population, then it can be problematic. But that's not really the case here. If we're sort of pretending that we're surveying Ventura College students when really we're surveying one class of Ventura College students, but you want that sample size to be up. Imagine the extreme case, a sample size of 1, right? You have a coin. Sometimes when you flip a coin, it's heads. Sometimes when you flip a coin, it's tails. So let's say you want to do a sample and you said, I'm going to do a sample of 1 coin flip, and then I'm going to use that to predict coin flips for the future. So you flip a coin, it comes up tails, and you go, okay, in my sample, 100% of the times I flipped a coin, I got tails. So that's my prediction, is that from now on, 100% of coin flips will be tails. Well, obviously that's ridiculous, right? But where was the mistake? Where was the mistake in that statistical reasoning? It was in using a sample size of 1, right? That's and it's extreme. We have more than that, but for the kind of work we're doing in this class, a sample size of 15 isn't going to cut it when you're trying to create histograms and stuff like that. It's not going to go well. So please sort of think about statistics in general and what you've learned so far, and realizing, oh yeah, a larger sample size is generally better. So we should apply that to the survey that we're working on in class here, the group project that everybody's working on. Okay. I was just going to say something that I forgot. Yeah. Okay. What did we have? Yep. So we talked about those, talked about that. Right. So you will be able to use StatCrunch going forward for quite a bit of this stuff. The further we go in the class, the more you're going to be using StatCrunch. So usually people figure out how to do that pretty well. I don't actually get a ton of questions from people using StatCrunch. And part of that is I think it's fairly intuitive. Plus, I usually show the class how to do it. So all you have to do is go back to the video and then watch what I did, and then you can do the same thing. But also, it's super easy to find on YouTube, right? You just Google StatCrunch Z-score, right? Like, so if you're trying to do a Z-score from home and you go, I don't remember how to do that on StatCrunch, just go on YouTube and search StatCrunch Z-score, and there's going to be endless videos showing you exactly what buttons to push in order to calculate that Z-score. So don't be intimidated by the StatCrunch. The StatCrunch is your heavy lifter for this semester. It's going to do a lot of the calculations for you. It's going to make a lot of your visualizations for you. So all you have to do is use it and put it to work. Okay? So last time we talked about, let's see, I forget which ones we did last time. But in the last few sessions anyways, we've talked about the measures of center, right? Measures of central tendency, this book calls it, and then measures of dispersion. So remember, measures of central tendency sort of helped us locate where the middle of our set was, in a sense, whatever that means, right? What does middle mean? Well, it turns out there's different interpretations of middle. And the mean is one interpretation of the middle, and the median is another interpretation of the middle, or central tendency. That's why they call it central tendency, because the word middle kind of gets us into a little bit of trouble maybe. But once we understand, okay, there's different ways of measuring the central tendency, right? And that seems weird. We like to have well, there's just one way to measure things, right? If I want to know how long this wall is, isn't there just one way to measure it? Not really, right? You could measure it in feet. You could measure it in meters. You could measure it in kilometers. There's different choices for how you do it. But even then, those measurements are all kind of done the same way. You take some kind of stick and you mark how many lengths of the wall, how many lengths of the stick the wall is long, and then you know if you're using meters, and you know how many meters the wall is. So even then, it's kind of the same way of measuring things. But think about okay, so here's an example, right? Here's the kind of thing we try to avoid in mathematics, and we also try to avoid in statistics, and that is, you get up and you hear, is Michael Jordan the best basketball player ever to play the game, right? And then people get in these arguments over who the best is. Well, it depends on how you measure the best, right? This is why these arguments are so silly, and it's why they work so good on, say, sports talk shows, because, you know, when there's sports channels, they have 24 hours a day to fill. So they can fill it with sort of meaningless arguments that are silly and don't mean a whole lot, because they're just sort of talking around in circles. They haven't even defined what they're talking about. So you say, okay, let's make a list. You know, we got, okay, Kobe Bryant, LeBron James, Michael Jordan, right? And you just fill out a list of the greatest basketball players of all time, and you ask, who's the best? Well, what a mathematician would say is, well, you have to define your metric, which means you have to define how you're measuring best, right? What one person measures best might not be what another person measures as the best, right? Is the best NBA player the person who scored the most points over their whole career? Would it be the person who has the best points per game? Would it be someone who's well-rounded, so maybe has high points per game, but also has a lot of assists? Does that make you better than someone who just scores every chance they get, right? For like, you know, like an Iverson who sort of always will take the shot versus someone else who's like assisting a lot more. Which one of those players is the best? So the reason that those arguments get silly on like sports channels is because they haven't even defined what they're talking about. They're literally talking about nothing, because what does best mean, right? You have to decide what best means, and then you can start applying things to it. So it's the same thing with central tendency. We have to define, what do we mean when we talk about the central tendency? And what we came up with is, well, there's two good ways to do it. There's the mean and there's the median. And how do you know which one to use? You got to play around with it. Statistics is a subject you just play around with the numbers, and it makes it super easy if you have something like StatCrunch, because you don't have to actually calculate the things yourself. You just tell StatCrunch to do it, and you can play around and go, oh, this is a case where I should use the mean, or I should use the median, or whatever, right? So then we also have multiple ways of measuring dispersion, but here it's a little more clear-cut. You pretty much will talk about the standard deviation 100% of the times that you do statistical work. Now, other things might come up as well. The range might come up. The variance might come up. These other things you might throw in there as well, but it's a little more like, those of you who go on to become professional statisticians, you might occasionally find a time where the standard deviation doesn't come up much. But a good rule of thumb when you're just learning this is always discuss standard deviation, and maybe discuss some of the other ones as well. If it's worth bringing up the range, bring it up. If you have a reason to talk about the variance, bring it up. Although we don't emphasize variance a whole lot in this class, because like I say, standard deviation is usually the right tool to be using in these situations. So we ended up with, okay, so now we know some ways to measure the center, whatever that means, central tendency, however we want to say it. We came up with some ways of measuring the spread of data, and these are things you should be looking at, right? A lot of times you're going to make a histogram, and it's going to look, you go, oh, that's kind of like a normal graph. It's bell-shaped and it's symmetric, but depending on how you set up your histogram, you might get a little bit different representation of that thing, right? Sometimes if you make your bin sizes smaller, all of a sudden you start seeing gaps show up, and then you go, oh, that's interesting. Why are there gaps right here at these certain ages or whatever? And then you can investigate those. So it's worth playing around a little bit with those. Once we have standard deviation, right? Remember, a standard deviation is a measurement that tells you how spread out your data is. So a low standard deviation means that your data is compact and tight together. A high standard deviation means that your data is very spread out, right? We looked at the bank teller lines and how they both had essentially the same middle, but the wait times were much more consistent for people. The wait times were much more consistent for people that were in the one line that then went to each teller versus having separate lines. The average or the mean wait time was about the same, but you had this big disparity. You had some people waiting a long, long time and some people waiting hardly any time at all. So that's how you want to make that interpretation. When you realize that your data has either a very small standard deviation or a very large standard deviation, just ask yourself, what does that mean? Oh, what we're looking at is a histogram of test scores, and the standard deviation is very low. That means the students largely scored about the same. Okay, that makes sense. Or if you have a high standard deviation, you could go, oh, students were all over the place. Like there were students that scored very, very high, almost perfect. There were students that scored very, very low, getting almost no points at all. And then you can interpret, you can try to use that interpretation of what you mean. So whenever you calculate something in this class using StatCrunch, just take a second before you move on and ask yourself, what does it mean? Like, what does this number actually mean to me? What is it telling me about the thing that I'm doing? If you don't ask that question, then you're kind of just running around pushing buttons, right? You have to try to interpret what's going on. I forgot to grab a water. Let me go grab one. I'll be right back. Sorry about that. Otherwise, I'm going to end up getting the hiccups if I can't. Okay, thanks. So once we have the standard the standard deviation is going to come up a lot in this class, and sometimes you're not even going to see it. But the standard deviation is built into many of the tools that we use. So for instance, when you calculate a z-score, and z-score is kind of a simple idea, but it does confuse students. So some students get confused by it, so don't feel bad if you're confused by z-score. But z-score is a perfect example of you're calculating this thing called a z-score, and if someone asked you, you'd say, well, I'm calculating a z-score. Okay, but what is a z-score? Oh, a z-score is the measure of how many standard deviations a data point is away from the mean. Oh, so you don't realize it when you say z-score, but the standard deviation is actually built into a z-score. So every time you calculate a z-score, you are necessarily dealing with a standard deviation, right? And that's going to happen throughout the course. Standard deviation pops up in ways that if you're not paying attention, you won't realize you're doing anything with a standard deviation because you put a value into StatCrunch and it spits something out and you go, okay. But what you don't realize is it calculated a standard deviation while doing that calculation. Okay, so standard deviation actually comes up more than you even think it does. And you're going to see it come up a lot, but you want to kind of look and realize, oh yeah, every time I do a z-score, I'm also doing standard deviations. Every time I do this hypothesis test, I'm looking at standard deviations. Like they come up regularly, okay? So it's one of the big things in statistics, right? It's kind of a big deal. So one of the first things we can do with the standard deviation is what's called a z-score. And z-scores are really cool, actually, because first of all, they're fairly simple. Some things in this class, the calculations get messy. For instance, if I had you calculate the standard deviation for a set with even like 20 data values, it would get annoying. That calculation would probably take 15 minutes, and it would be super annoying to go through and do, right? Or the line of best fit. That's an annoying calculation to go through and do. It's doable by hand in 10, 15 minutes, but it's annoying. Z-scores are like the simplest formula. They're so easy, and one nice thing about it is the formula is so simple that you can look at it and go, oh yeah, that's what it is. So it's not like, if I hand you some of the formulas that we're going to see in this class and say, what does this mean? It's totally reasonable that you'd get stuck in the math and go, I'm confused. I don't know what's going on. But the z-score is such a simple calculation. All you have to do is look at it and go, oh, that's right. It's just the number of standard deviations it is away from the mean, right? Which is important because it allows us to compare some things that we have no other way of comparing, right? So let's look at an example here. Let me show you what a z-score is. So first, let's discuss a z-score. Z-score. Right? Pretty important and also just kind of cool. So, all right. So I was going to say something, but let me skip that. I don't want to confuse things. Z equals. Actually, let's put it in that format. Oh, hold on. I forgot to do how to do X bar in LaTeX. Hold on a second. Oops, let's see. I got to get this right. So this is. Here we go. Okay, z equals x minus x bar over s. So, what are we looking at here? What does this mean? Now, I said it's a simple formula, and you can look at it. It pretty much is, right? In fact, most of you could probably memorize that by the time we're done today. You go, z is equal to x minus x bar over s. Now, you might not remember what that means. Hopefully, you will, because like I say, once you get comfortable with it, you can just read it and go, oh, that's right. That's what a z-score does. Oops, let me shrink this down a little. A little easier to see there. So the z represents our z-score. That's a measurement. Now, the measurement of a z-score is a little different than what we've been doing so far. Remember our last few measurements, the mean, the median, and the standard deviation? Those are the big ones we talked about. Those are all measurements on an entire set, right? So in other words, I don't take one test score and then say, what was the mean of this one test score? It doesn't make sense to take the mean of one thing. It's just going to be that thing, right? So notice the mean applies to a whole set. The median applies to a whole set. The standard deviation applies to a whole set. The z-score is a measurement of a data point. The z-score is not a measurement of the entire set. It is the measurement of a point, a data point inside the set. So each data point would have its own z-score. So for instance, let's take project scores, right? At the end of the semester, you'll all submit a project. I will grade it, and we'll have a list of scores. Now, I'm not going to analyze this in this way. I'm just giving you an example. We could take those test scores and take the whole set, and we could figure out the mean. We could figure out the median. We could figure out the standard deviation. But each individual data value would have its own z-score. In other words, each of you would have a z-score. Your own score would have its own z-score. Does that make sense? Some students kind of struggle with this because they start thinking about, we're doing these measurements on a whole set, and then the z-score throws them off because the z-score is a measurement of the data value in the set. So some of you on your project, you might be 2 standard deviations above the mean. Some of you might be 1/2 standard deviation below the mean. One of you will probably be 1/3 of a standard deviation above the mean. Do you see how it would be different for each person? Because the z-score is just a measurement. It's like instead of using you've done this where you measure things with a ruler and you just put the ruler end to end and you go, oh, this is 3 feet long, right? Well, that's what you're doing with the z-score is you're taking the standard deviation as your ruler and you're measuring how far is this data point I'm concerned about from the mean, right? Which is why this is actually a great way for test scores. Students always want to know the mean test score, and I've talked about why that's not a good measurement, but a z-score would be good. A z-score would be a really good way of seeing where you fall in the classroom, right? And I'll actually do an example like that in a minute. So what essentially what the z-score is you take your ruler, right? Sort of, it's not a physical ruler, just sort of imagine that, and it's the standard deviation, and you're saying, well, my test, the average was 67 and I got an 82. So you're measuring how many standard deviations to get from 67 to 82, and that tells you your z-score. And we can see that right here, right? This x right here, remember your notation, this x represents a data point. It can be any data point you're concerned about, because remember, for each data point, we'll get a different z-score. So this is a data point. X bar is the mean. So we have to calculate the mean and also the standard deviations to do a z-score, but a z-score is a specific measurement to a data point. So what is x minus x bar? That gives you the distance between the data point you care about and the mean, right? When you subtract two things, that gives you the distance in between them. And notice it's nice because the sign of the z-score tells us direction. If you have a positive z-score, what does that mean? That means that your data value you cared about was bigger than the mean. So like with test scores, that would mean that you scored above the mean. Okay. If this is negative, that means your data value was below the mean. So that would mean if you get a negative z-score, that would mean you scored below the mean. How far are you below the mean versus how far are you above the mean? And then we divide everything by s. That's the standard deviation. So you're taking the distance between the mean and the median, and you're dividing by s, which tells you how many standard deviations you were away, right? So imagine that you made a measurement on your wall between two, like say a light socket and the other end of the wall, and you measured that in inches. Well, if you divide it by 12, that gives you feet, right? So that's like this. So instead of dividing by 12 inches to get 1 foot, we're dividing by the standard deviation to decide how many standard deviations away we are, okay? So if you calculate a z-score and you get 1.3, that means your value is 1.3 standard deviations above the mean. And then someone else calculates another standard deviation for a different point and they get 2. That means that data point is 2 standard deviations above the mean. This can be helpful for us for a number of reasons. This is one way that you can tell if something's an outlier. There's kind of different rules of thumb depending on which book you're working in, but sometimes books will say if you're higher than 2 standard deviations above the mean, so in other words, your z-score is bigger than 2, that's like a point of interest. We should look closer at those points and ask ourselves, is something going on here? And then a lot of times if you're more than 3 standard deviations, they'll start calling that an outlier. We talked about outliers before and talked about how outliers they're data points that are off far away from the data, but we didn't have a really good scientific way of telling if something was an outlier. We could come up with a graph where there was a data point off to the side, and some people might go, I don't think it's that far away. I don't think we should call it an outlier. And someone else would say, I don't know, it seems pretty far away. Let's call it an outlier. Well, how can you scientifically decide if it's an outlier or not? Well, you make a decision. Okay, for this project, we're cutting off outliers at this data, right? Depending on what you're doing, what you consider an outlier, if you're trying to do quality control of bolt manufacturing, you might have one z-score that you anything above that you call it an outlier. And then if you're doing something completely different for some kind of a social awareness campaigning, but you're taking data along the way, your what you consider an outlier might be different, but you should define it. That way everyone knows. So we might say, okay, well, in this case, anything above 2.5 standard deviations we'll call an outlier. So like when you take this class in the books, a lot of times we give you a specific rule and says anything above 3 is an outlier or anything above 2 is an outlier. It just depends on the book you're using. But just kind of realize in real life, that's actually one of those cases where you kind of have to, it depends on the problem that you're doing, right? Which I know it sounds like a broken record sometimes, and students don't like these kinds of answers that are uncertain. When they ask a question, I say, well, it depends on the problem you're working on. Like, that's not a very satisfying answer, but it's also part of what makes statistics a little more interesting. So, pretty simple formula. Even if you had to calculate z-scores by hand, any single z-score isn't going to be very, very complicated, right? So, let's do an example of how this is interesting, because we can use this tool in a way that we cannot use other tools. So let's go into StatCrunch, and let's say we've got So an English class and a math class. Right? In fact, let's call this English. Let's make up an imaginary case here. So English, and this person in this class is named John. And then this is math, and this person in this class we'll name Malcolm. Okay, so we have, oops, let me move this over, kind of see where it's going to be convenient. Okay, so just kind of follow along. These are just an example to help you understand. I'm going to go through some stuff, and hopefully by the end of this example, you'll understand what a z-score is and some interesting ways in which it can be used. So this is not to say this is the only way to use z-scores. It is not. But this is one example that I find a little bit more interesting just because I don't know of any other way you'd do this problem. Right? But z-scores end up getting used in other calculations along the way. So don't think this is like the way to use a z-score. This is just one of the many ways to use a z-score. Okay, so John and Malcolm are friends, right? And they're going to college, and they work hard, and they try to get good grades on their exams, and they try to get good grades in their classes, and they're a little bit competitive, right? And in a good way. It helps them push each other. They both want to be able to say they're the best, and so they work a little harder so they can give their friend the business, right? So that's John and Malcolm. John's in an English class, and Malcolm's taking a math class. And they both just had big projects due, okay? Now, John scored the best score in his English class, and Malcolm scored the best score in his math class. And so they're both doing pretty good. Right? But, you know, two friends giving each other the business. They want to know who did better, who got the higher achievement. Okay, so let's come up with some scores. So let's just say that John got a 92. And then here's the remainder of the scores for his class. So there's what, like an 87, a 65, a 60, or a 61, 54, 73, 81, 72, 74, and let's make it 77. Okay, so those are the test scores that for John's class. Okay, now here's Malcolm's class. So he got 95, or 96, we'll say, and then what? There's maybe an 89, a 91, 77, 80, 83, 89, 90, 74, and 81. Okay, so John and Malcolm, they both, let's see, I can make this a little bigger, I think. There we go. That looks a little better. So we've got the English scores for John's class. We've got the math scores for Malcolm's class. And John scores the one at the top of his column. Malcolm scores the one at the top of his column. Okay. So back to our question of, well, who's better? Who did better? Who do you think has bigger bragging rights in this situation? And you could say, well, so Malcolm comes in and says, well, I got a 96 on my math project, and you only got a 92 on your English project. So that means I did better than you. I beat you because I got a 96 and you got a 92. But John is saying, well, yeah, you scored higher, but look at most of the scores in your class are higher. So even though you got a higher grade, most of the grades were already higher. So you didn't outperform your fellow students as much as I did. I got a 92, but most of the other scores in my class are like kind of in the 70s. So both of them are making reasonable arguments about who did better, right? So how can we apply statistics in a way to say, I think this person did better? And one way of doing this, which actually is quite effective, is a z-score, right? We're going to figure out the z-score for John's 92, and we're going to figure out the z-score for Malcolm's 96, and whoever did better scored more standard deviations above the mean, meaning they did a more sort of a more rare job, I guess you could consider. A lot of times when we talk about probability, we're going to talk about rarity. How rare is an event to occur? In this case, we can figure out whichever one is further away from the mean, assuming they should both be in the positive direction since they have the highest score. How many standard deviations above the mean did they score? And that takes all the things we just talked about into consideration. That takes into a fact that one of the scores is bigger than the other. It also takes into account all of the scores in the class in this calculation, so you can put all that together and decide which one of these is more unusual. In math and statistics, when we say unusual, that doesn't mean weird or strange. It just means which one is less expected than the others. So let's do that. I'm going to go through. So, and this is something, remember, we've got something coming up is our summary stats. That's in your, if you look, 5-number summary and box plots. That's coming up in chapter 3. So some of you are probably already working on this, hopefully, that 5-number summary. So you can get that in StatCrunch by going to the summary stats, and we want columns because each of our columns is considered a set. So I go columns, and it says, do you want the summary stats for John's English class, or do you want the summary stats for Malcolm's math class? And I was like, well, first let's do John's English class. And group by, we don't want to do that. And then remember here, you can choose which things it calculates. You can pick more things. You can pick more things here than our, so like if you didn't want to know the standard error, you could oops, it just, darn it. It just clicked it. That's not what I meant to do. Okay. So we should be able to, let's see, I can go back down to, so anyways, I just clicked them again. There's a way to, oops, I'm going to have to mess around with that after class to figure out how to do that. But I just messed it up by trying to be a little too fancy. So let's go back. Summary stats, columns. I'm just going to pick John's English one. And it's got all the stuff we want. Mean, variance, standard deviation, median, range, all that. So it's actually giving you more than just the 5-number summary. So I hit compute. It gives me this, which I can shrink down. And we can put it sort of up here for now. Let's see, where do I want to put it? Let's put it there. And we can see this gives me lots of information. Mean, median, standard deviation, range, number of values, all that kind of stuff. So we now have that for John. So let's calculate John's z-score. So here's what I need. I'm going to make a note and say, okay, well, what was the mean and what do we need for that z-score? We need a standard deviation and we need a mean. So I'm going to say, okay, so I'm going to make a note here for John. His mean is 73.6 and his standard deviation is 11.568. Right? So remember mean, and this one's the STD-DEF, that's standard deviation. Okay, so I made a note of those. So now I'm going to do a calculation remembering, oh yeah, and what was John's score? 92. Okay, so I come over here. So John's z-score would be so it's x. Remember, x is the data point in question. For us, John got I already forget, was it 92? 92. Okay, so his data value that we care about is 92. And we're going to subtract from that the mean, which is 73.6. And then our standard deviation is 11.568. So that's his z-score. So you could just do this on a calculator, right? In fact, let's do that. Is my calculator open? No, I had it open yesterday, but. So make sure you use your order of operations and that you're using your calculator comfortably. A lot of students, it's very weird. Calculators are very different. You'd think there'd be a standard in calculators, but anytime someone hands you a calculator, there's almost always a moment of confusion where you're like, oh, this is different than other calculators I've used before. So just make sure you're comfortable with them. Even simple calculators like this can be, a different setup than what you've seen. So I'll do 92 minus 73.6 equals 18.4 divided by 11.568 equals a z-score of 1.5. Does that make sense? Yeah, that looks right. Okay, so John's z-score then is 1.59. 1.59. So John scored 1.59 standard deviations above the mean. Okay, so now let's check Malcolm's z-score. So we're going to get, let's fill in his stuff here. Okay, so let's get rid of this. So now we want to calculate Malcolm's z-score. So we're going to go back to our stats, summary stats, columns. This time I'm going to choose Malcolm, and we're going to compute it. And I'm going to make a note here for Malcolm. Say, okay, his score was 96. His mean was 85. And the standard deviation was 7.023. See how all those values are very different than John's? So it's really hard to compare these without the use of a z-score. Okay, so then I come in here, and that means that his data value is 96, because that's what he scored. You could calculate it for any of them, but we're just concerned about his particular score. 96 minus 85 over 7.073. Is that right? Yeah. So bring back my calculator. Where did it go? Calculator. And we'll go 96 minus 85. It's 11. Ooh, these are going to be kind of close, aren't they? Divided by 7.073. Ooh, those were closer than I intended them to be. 1.55. So this one's close. Actually 1.56 if we round it. I'm surprised it came out that close. I was trying to make them a little lopsided when I was doing this. 1.56. So essentially, they both did really, really well, and they did almost the same. But technically, John's z-score is a little bit better than Malcolm's z-score. So you know how it is when you're young and sort of young people giving each other the business. It doesn't matter. They both did well. It's more about who has bragging rights, right? So John can say, hey, I beat you. I did better compared to my classmates than you did compared to yours. They both should feel good. They both did outstanding. But see how we were able to measure this? Any other way of trying to argue this, it just ends up like those sports arguments on the 24-hour sports channels where they go in circles talking about like things in an unscientific way and just saying, well, I think this guy's the best player because he's really exciting to watch. And they just kind of thrown out this stuff, none of which is scientific. We were able to scientifically say, yeah, we can back up that really John's is a little more impressive than Malcolm's score, right? Although kudos to both of them, even though they're imaginary, right? Okay, so z-scores, very, very useful in that way. Very, very helpful. I got it. In my opinion, z-scores, one of my favorite things in stats because it's such a simple idea, such a simple formula, and yet so easy to compute into, oh, I get what it means. Right? We can understand the standard deviation is a length. It's how spread out our data is, right? I shouldn't say it's a length, but it's a measure of how spread out our data is. But there's a little bit in there in the calculations that, gets a little hard to follow. With the z-score, it's sort of like brilliantly simple, right? Oh, wow, what a cool thing. And we can take two totally different things and measure them in a way that is otherwise very hard to compare, right? Very useful in that way. Okay, Can I talk about percentiles in 4 minutes? Actually, there was one other thing I wanted to talk about. Oh, so generally in books, they'll kind of say once your data value goes 2 standard deviations away from the mean, those are what we call significant, which means take a look at them. There might be some information or some questions you can ask about those data points that show you special information, right? Sometimes by looking at how something is different from the group, that also gives you an indication about how the rest of the group is the same, right? These are the kind of ways you need to look at things when you're doing statistics. Oh, this one person scores way off to the side. I wonder why they're so different than everyone else. And it could be, well, this one student did almost no studying and the rest of the class studied pretty hard. That's why this is one really, really low score and the rest are kind of bunched together around like 85, right? You can investigate and try to come up with reasonings by looking at those significant values. And usually if you're 3 or more standard deviations away, most people would be comfortable calling that an outlier, right? You might for other situations, you might be able to get away with even if the z-score is below 3, you might call it an outlier. It's one of those things where people define outlier a little differently for different settings, but a good rule of thumb is 3 standard deviations away, or sometimes 2.5 or something like that. Okay. All right. Looks like I'm out of time, so we will talk next time. I keep forgetting to mark my place. I'm going to mark my place here. I'm going to explain percentiles next time because percentiles, students find very confusing percentiles. So we'll talk about that a little bit and try to make sense of what those are. Good news, StatCrunch will calculate this stuff for you, but we'll talk about that next time. Okay, so I need to see, so almost everyone signed up for the homework. That at this point, if you're not signed up for the homework, you're probably not participating in the class, so that's good. We've got 35 people signed up and participating in homework. Please, by Wednesday, if you can help it, try to get that survey taken. The sooner I can release the results, the sooner that some of you will start doing your work, and it will lead to a better semester for you. So please try to get that done. We need, at the very least, we need to double what we have now, and it would be really good if we could get to all 35 people having taken it. Plus, trust me, it's just the more data points you have in there, the easier it's going to be for you to actually do the work you need to do on the statistics. It's going to be easier for you to see the patterns, the shape, all that kind of stuff. So help out your fellow student. To those of you who already did it, the 15 of you that already took the survey, great job. You're sort of leading the pack as far as being responsible and doing what you need to do. The rest of you, the other 20 people, please get in there. Recognize that this benefits all of you. When you take the survey, it benefits you yourself. It also benefits the other 34 people that are relying on you to take that survey. Okay. Unfortunately, there's no way I can find where I can grade you on the survey because I can't actually tell who took it. And also I don't want to have your names in there because I don't want people to be nervous about answering honestly because they think, well, what if someone knows my name and they also know how I answer, whatever, if there's social questions in there about gender or any kind of thing like that, people might be afraid to put their true answer down if they can be tracked back. So I don't throw names in there. Just because, and that was just an example. Lots of reasons why some people might not they might not answer honestly because they don't want their personal information out there if they can be identified. So I can't really give you points for doing the survey, but it's one of those things like just do it because it's better for all of you, right? You're sort of helping out the whole class by doing it, including yourself. So try to be a good person, right? Good human. Okay. I'm going to shut down the YouTube stream. Anyone who wants to talk to me, hop over into Zoom. We have office hours, and I will talk to you about whatever you want. All right, thanks, everybody.